In this video, section 4.2a, as well as 4.2b and c, we will focus our interest into the nucleus of the atom. Nuclear chemistry is the study of the changes of the nucleus within atoms. Ordinary chemical reactions involve the loss, gain, or sharing of electrons, but nuclear reactions only involve changes within the nucleus. Recall that the nucleus has protons and neutrons inside of it. Collectively, these two subatomic particles are called nucleons. Remember that the mass number, which is the number in the upper left corner, represents the number of protons and neutrons within the isotope. The lower number, the subscript, is the atomic number, and it tells you how many protons you have. It also identifies the element. No two elements can have the same atomic numbers. Of course, the symbol of the element will identify the element's name. Most nuclei are stable, which means they hold together well. An unstable nucleus is not going to hold together well and will go through a process of decay in which it will break down, releasing particles and/or energy in order to become stable. We call unstable nuclei radioactive. There are several ways radioactive atoms can decay into different atoms. Transmutation is the first process. This is a type of nuclear reaction where the number of protons within the nucleus will change. And so that will also change the identity of the element. A new element will be created. We say that a parent atom will then create a daughter atom. There are three major types of decay that you need to know in this class. The first is alpha decay. An alpha particle is basically a helium nucleus. It is represented by the symbol He with a superscript of 4 and a subscript of 2. Remember that the superscript kind of represents the mass and the subscript represents the number of protons. A more authentic way to write this would be to use the Greek symbol alpha and place the 4 and the 2, respectively. The penetrating power of alpha decay is extremely low, so it is the least dangerous of the three types we're going to discuss. This is because it is the heaviest of the three particles. Clothing or thin paper can block these alpha particles and protect you. If we take a look at the example below, you can see a nuclear equation showing alpha decay. Notice that the alpha particle is on the product side. It has been released. And you can see that the new particle that has formed is 4 less than the mass number of the original parent atom, and it's 2 less in terms of proton number. Once we subtract 4 from 238 to get 234, and 92 minus 2 to get 90, you can use your periodic table to discover who the identity of the new daughter nucleus is. In this case, it is thorium. In this diagram, you can see the same example. Notice that now we're focusing in on the proton and the neutron numbers within the nucleus. 146 and 92 does total up to 238 as the mass number, and of course the number of protons is 92. When we release the helium nucleus, once again you can see that's on the right hand side, you will see that the atomic number decreases by 2 and the entire mass number will decrease by 4. 2 are being removed from the nucleus, from the protons, and 2 from the number of neutrons, as we have 144 neutrons. That's really not that important because that totals up to 234. In the second representation, you can see that there is a unstable nucleus on the left-hand side, and as it releases once again the alpha particle, it creates a smaller, more stable nucleus. The identities of these two particles are not known because of the inability to calculate the protons and neutrons based on this diagram. The next type of decay is beta decay, and that will be when a nucleus loses a beta particle. A beta particle is basically a high-speed electron. So there's two ways that we can write its symbol. We can use E for electron, or we can use the Greek symbol for beta. Notice that the mass number is 0, and that's because electrons really don't have a significant mass. They do have mass, but not significant, and that it is negatively charged, and the -1 goes down in the lower portion. The penetrating power is a little bit more intense for beta particles. They move faster, and so they're a little more dangerous. We need something more substantial to block them, and so thin metal or wood is usually what we would use. In this example, you can see that iodine is going through beta decay. It is releasing the beta particle, and as it does that, it produces a new daughter nucleus where the mass number stays the same. Just like before, we're going to take 131 minus 0, which is from the particle, and that gives us 131. 53 minus -1 actually gives us 54. When we look on the periodic table, we will see that the new identity of the nucleus is xenon. Notice that the mass did not change, but the atomic number increased by 1. So that's really important to be able to recognize. Now, why did that happen? Well, I need you to understand that a neutron is really a proton and an electron that has been slammed together. In beta decay, a neutron is splitting apart and is becoming a proton and an electron. The electron does not have any business within the nucleus, so it gets ejected out of the nucleus, leaving the proton behind. So that explains why the atomic number is increased by 1, but the mass number stayed the same, because it was kind of you lost a neutron, but you gained a proton. In this picture right here, you can see that we have thorium-234, and once again, we're really focusing in on the nucleus. You can see that there are 90 protons, and there are 144 neutrons. That gives us a total of 234 as our mass number. As the high-speed electron is removed, you can see now that the atomic number increased by 1. That's why the substance has changed. The identity of the atom has changed to palladium, not protractium. But the mass number has stayed the same. In this last picture of beta decay, we're going to look at the lithium atom. Notice that it has a mass number of 7 and an atomic number of 3. So there are 3 protons, and then there are 4 neutrons. In beta decay, remember that a neutron will split apart into a proton and an electron, and that electron has no business being in the nucleus, and so it gets ejected out. You can see that happening in the second phase of this diagram. When we look at the aftermath, you will see that you still have 7 as your mass number, but 4 protons now exist. And so that has changed the identity of your atom, but it kept the mass number the same because there are still 7 protons and neutrons combined. The last type of decay is called gamma decay, and gamma decay is really the removal of high energy radiation. We represent the gamma radiation with the Greek symbol of Y, and you'll notice that it has a mass of 0 and an atomic number of 0. And that's because, once again, gamma is really energy. It is not a particle. It doesn't have mass. The penetrating power is extremely high. This is the most dangerous of the 3 types of decay, and you really need to be behind super thick metal or thick concrete in order to protect yourself from this type of decay. In the example below, iodine-131 is going through gamma decay. Notice that it will release gamma energy, and the particle that it creates is the exact same particle. So we're not changing the identity of the atom in gamma decay, we're just releasing some of that high energy that is found within the nucleus to make it more stable. Gamma decay is usually a form of decay that happens after a particle has gone through alpha decay or beta decay, or positron decay or electron capture, which are the other 2 forms that we're not going to discuss in this class. Last but not least, we have a quick visual diagram here that will show us that paper can protect you from alpha particles, but not beta. A small, thin piece of metal can protect you from beta particles, but not gamma. You really need a really thick layer of lead or concrete to protect you from gamma. Let's try a few out. To write a balanced nuclear equation, you must make sure that the atomic number and the mass number on both sides of the equation are equal. So let's start off with the first one, alpha decay of thorium-230. So we're going to go ahead and write the symbol for thorium, which is TH. The mass number is 230. And the atomic number is 90. We're going to draw an arrow to represent yields, or to produce. And since the alpha particle can be represented as 42He, we'll put that on the product side. 230 minus 4 is going to give us 226. 90 minus 92 is going to give us 88. And then we're going to identify number 88 on the periodic table. And that will be radon. For our second example, we're going to take cesium-137. So we're going to look up its symbol CS. We know its mass number is 137. And you can see right here that it has an atomic number of 55. We're going to draw our arrow. We're going to release our beta particle. Remember, it looks like 0, -1 E. And we're going to do the math. 137 minus 0 is 137. 55 minus -1 is 56, which, if you look on the periodic table, is barium. All right, I want you to take an opportunity now to try 3 examples on your own. Come back and look at the answers to make sure that you've done them correctly. Okay, for the first example, beta decay of zirconium-97, you can see that on the right-hand side, I have put the beta particle. 97 minus 0 is 97, 40 minus -1 is 41. We're looking up the new identity of number 41, which is niobium. For the second example, alpha decay of americium-241, we're going to put the alpha particle on the right-hand side. 241 minus 4 is 237, 95 minus 2 is 93, and then we're going to go to the periodic table and we're going to look up who number 93 is, and you can see that's neptunium, Np. In the last example, alpha decay of uranium-238, you're going to put the alpha particle again on the product side, and you can see that this time I'm using the authentic alpha symbol instead of the helium symbol. It still has a mass number of 4 and an atomic number of 2. 238 minus 4 is 234. 92 minus 2 is 90. And if we look up who number 90 is, you can see that that is thorium. In the last example, you will see that I did not actually give you what kind of decay it is. In this case, you have to figure it out. We know that 239 minus 239 is 0. 93 minus 94 is -1. And out of the 2 particles, alpha or beta, you can see that that is going to be an example of beta decay. If you were wondering where I got the numbers in the lower left-hand corner, because they were not given to you in the problem, remember those are the atomic numbers, and you can always go to the periodic table and take those and put them right in the nuclear symbol. On a side note, there are a bunch of transuranium elements. These are the elements that have an atomic number larger than 92. They have all been created through the process of nuclear transformations. And we'll take a look at a picture of that on the next slide. But basically, they've been made through the man-made process of smashing atoms in nuclear accelerators. You can see an example here. If we take uranium-238, and in that nuclear accelerator, we smash it with a neutron, it ends up producing uranium-239, which then goes through beta decay to produce neptunium-239. So this is a way that scientists can create new elements. Any element after number 92 on the periodic table has been created in this way. It is not a naturally formed element, but a man-made element. On this screen, you can see a picture of a particle accelerator from the sky view. You can see that they are very enormous. They have circular tracks, and they are miles long. In the upper right hand corner, you can see a more schematic view of what would be underneath and under the ground. And basically, once again, these transuranium elements are being created by accelerating particles and colliding them with nuclei to form new substances, new elements.